Hey everybody, this is the last chapter in statistical concepts. So this one will be on the differences among groups, and this is one of the areas most of you or many of you may use if you have a control experimental groups and then different treatments like pre-test, post-test, or repeating those measures over different days. So the purpose of the statistical test is to evaluate the null hypothesis at a specific alpha level. P minus 0.5 or 0.1 are the two most common. And then the question you're going to ask is, do the two levels of treatment differ significantly so that, again, the chances are not attributed to chance? If it's 0.05, we have already talked about that. It's that chance could occur no more than 5 times out of 100. Now, for the different tests we're going to talk about, they either reject or fail to reject the null hypothesis. They don't accept the research hypothesis. I know that sounds like, like it's not correct or it seems haphazard or whatever, but by definition, these different tests we're going to talk about reject or fail to reject the null hypothesis. We'll also remember that these statistics can only determine whether groups are different. They don't say why they're different. That's left up to previous research, your lit review, and your methodological design, and any logical interpretation of the literature. And that includes unbiased interpretation of the literature. So you don't really want to just know if the statistic is significant, but you also want to know the strength of the association between the independent variable and the dependent variable, or the size of the difference between those two groups. And we're going to talk about that, and that's the effect size. So as far as differences among group values, many times what we'll use are our values, or T or F ratios. And they're typically found in appendices or when the software, you click t-test or ANOVA, they'll calculate the T ratios and the F ratios for you. And then again, the meaningfulness of the differences are dealing with the effect size. In order to use the T and F ratios, there are 4 assumptions that you have to consider. And those are: the observations are drawn from normally distributed populations, so you have to have that bell-shaped curve or normal distribution. The observations must represent random samples from populations, so you took a random sample from the population. The numerator and denominator estimates of the same population variance, and the numerator and denominator F and T ratios are independent. And that just deals with the formulas that you'll learn in statistics. As far as t-tests, there are 3 kinds of t-tests, and we're just going to briefly talk about them, and we'll talk a little bit about the one that's most commonly used. The t-test between a sample and population mean really isn't used that much because you have to take the population mean, and it's very challenging many times to get that mean. So again, this one's not typically used. The one that's most frequently used is the independent t-test. It determines whether 2 samples means differ reliably from each other. For examples, do 2 groups training at different levels of intensity, 40 and 70% of VO2 max, differ from each other on the measure of cardiovascular endurance? So we're looking at cardiovascular endurance and then 2 treatments, 40 and 70% of VO2 max, and then the outcome is the distance run. So when you look over here, or the formula for independent t-test is the formula you see here, so I don't have to really say it fully, but when you look over here on the chart, which is from your textbook, the T here is the mean of group 1 minus the mean of group 2, and then you take their standard deviation squared and then their number of subjects, and then that gives you a 13.73 T ratio number. You would basically take that into your book. There's tables that have been created, and they are at the end of your book. You look at, this is degrees of freedom, T minus, or D n minus 2. So it's 30 minus 2 because you have two groups, 15 and 15. And then you would look to see if that value in the book is greater. Now, you won't have to do this because you'll most likely do this on a computer. It will spit out what the T ratio or T value is and its alpha level. So this, if we did a 0.05, this would be significant because our p-value is 0.005. And so how you would write the outcome is T28, again, just like you see up here. The T ratio, the value, this is not the mean, this is the value that you calculate. All right, and then the P of that would be it should actually say 0.005. All right, you would label that. Dependent t-test just means that there are two groups of scores that are related in some manner, whether two groups of participants are matched on one or more characteristics, and they're not independent, or there's one group of participants is tested twice on the same variable, and the experimenter is interested in the change between those two groups, and that's usually a pre-test, post-test, but there is no control. It's just a pre-test, post-test on a group. So don't think of this as you're taking a pre-test, post-test and comparing control and experimental. That is not the case. It's one group, pre-test, post-test. As you can see up here, pre-test, post-test, and then the different subjects. There is no control. And you would calculate this. That's why this isn't most commonly done in the research that athletic trainers do, because we're usually taking a pre-test, post-test type of measure. Now, interpreting the t-tests, you can do a one-tailed or a two-tailed t-test. Basically, a two-tailed assumes that the differences are going to occur in two different directions from the mean. So if you look on the picture on the right, it's the picture on the right where it says two-tailed, that you know that the changes could go one way or the other from the mean. However, most of the time we can predict a direction from the mean. Like for instance, if we are hypothesizing one group is better than the other second group, then we would use a one-tail because we know that the scores are going to get better or they're going to get worse. We just know that they're not going in both directions. We're hypothesizing that they'll go in one direction. So most of the time what you would see is a one-tailed t-test. So the next type of statistic we're going to talk about is an analysis of variance. And this allows for the evaluation of null hypothesis between two or more group means. It is an extension of the independent t-test, all right? But again, that was one group with two different measures. Now you took one group, pre-test, post-test. That's what the t-tests were for. It is used when there's two different levels as well. So not only do we have maybe two different groups, but we have two different levels. And you'll see what I mean here in a second. So if we want to assess the average athletic performance between three groups, we got group 1, 2, and 3. That would be our three different levels. So the statistical test is the F-test or F ratio. We'll talk about what the 2 and 110 means a little bit later in the presentation. But basically, again, we can look at the between groups and within groups. And there's different types of ANOVA. There's a simple ANOVA, or also known as a one-way ANOVA. There's a factorial ANOVA. You might even see it sometimes called a two-way ANOVA or two-way factorial ANOVA, and the ANOVA with repeated measures. So the simple ANOVA looks at three different groups. All right. So it's basically, if you look at the picture, it's three different groups, but it's when one factor or one treatment variable is being explored and this factor has more than two levels. There is only one treatment factor. So if you look in the picture on the right, the factor is language development test score. That's the one treatment factor. We're just looking at the language development test score over 5 hours, 12, 10 hours, and 20 hours of hours per week of work. Variance is due to difference. Performance is separated into variance due to differences between the groups, or variances due to within groups. And this is important to think about when you start doing these. What you're looking at is between groups and within groups. Within groups is those differences within that one group. It does not look at comparing the other two groups. If you look at this picture, when we're interested in the comparison from group 1 to group 2, group 1 to group 3, group 2 to group 1, group 2 to group 3, group 3 to group 1, and group 3 to group 2, then we're looking at between groups. And many times that's really what we're interested in, is how are the groups differing between each other, not within just group 1, or within just group 2, or just within just group 3. And this one would be mapped as a 1 by 3 simple ANOVA, or one-way ANOVA. Then you have your factorial ANOVA, again sometimes called a two-way ANOVA or two-way factorial ANOVA. This is a little bit more complex. It uses more than one treatment factor. So now, instead of just having our 3 groups and just interested in each groups as a whole, whether male or female, they were just thrown into a group 1, language development test scores. Now we're splitting it male versus female. All right, and now we've just added a treatment factor, male and female. You could map this out as a 3 by 2 ANOVA, where there's 3 levels of one grouping, and then there's 2 levels of other groupings, and that's male versus female. Many times what you'll see with a two-way ANOVA is what you see on the bottom. It's a 2 by 2 factorial ANOVA, where you have a control and experimental group and a pre-test and a post-test group. And that's fairly common in the research that we do. So you could use t-test for this, but again, the t-test may not look at the between group differences. So let's talk about the main effects and interactions. Main effects are the effect of a single independent variable on a dependent variable, ignoring all other independents. So really, what does that mean? So if you look at the table over here, and we look at what we're considering as main effects, and we look at exercise main effects. Basically, you look across exercise yes, no. You look across to those means 14 and 4. All right, and those are the main effects. So basically, without anything else, all right, weight loss is better with exercise than without exercise. Same with dieting. Now we can look down instead of across, and just dieting, yes, no. You can get more weight loss with dieting than without, because if you look down, diet, 15 people, we'll say 15 lost 15 lost weight, versus when people didn't diet, only 3 as a mean lost weight. So really, each main effect only looks at the marginal data. It's kind of looking at the within group differences like we talked about in the previous slide. These are the marginal means. They do not look at if one group, the between group differences. So when we want to do that, we're looking for interactions. We want to know if one group is affected or influenced by another group. It'll assess whether the different conditions for an independent variable, yes, no, produce results that differ depending on what condition you consider. So if we look over here, we want to know if weight loss depends on exercise, a diet, or both. So in essence, we'll look at the interaction to see if both diet and exercise will affect weight loss. So we look at across if it's exercise and diet, so we'll look at the 2 yeses. Yes and yes is 20. Yes and no is 10. for diet and exercise. For no diet and exercise, it's 8. For no diet and no exercise, there's minus 2 pounds of weight loss in essence. So it looks between the groups. All right, these are the interactions in these types of tests that we're interested in most of the time. We're really not, I can't say we're not interested in main effects, but we're predominantly interested in if one is influencing the other. So when we plot main effects and interactions, if we look at the significance and non-significance when we plot our means, all right, if you see on the picture on the left, if the bars cross, so high fit, low fit, mean, attitude scores, if those lines cross, that means there's a significant interaction. If they don't cross, like you see in the middle picture, it means that there was no interaction, no significant interaction between the two groups, high intensity, low intensity, and their scores. And then if you look at significance in one group but not the other, so this means that there was a significant main effect from, we'll say, I don't know, pre-test to post-test, but the straight bar that you see, there was no significance within that group, within the high fit group. So you can plot these. So if you do this in statistics class, or you see this in a printout, you'll see that if there's a significant interaction, the bars will cross. If there's not, they won't. They'll be parallel or something like you see on the right. Now we're also many times interested in repeated measures ANOVA, and this is now basically a repeated measures. In other words, you're taking a pretest and then you're going to measure whether it's 1 hour, 2 hours, or 1 day, 5 days, 10 days, 30 days. You still have 2 different levels, control and experimental, but then you have 3 different groupings as you go out for the repeated measures. So when you interpreting the F test, when you get that printout, all right, and when you actually write it out. So what you'll see when you write it out is F is 2,27 equals 8.8, and then the p-value of less than 0.05. F represents that it's the test statistic. 2 and 27 are number of degrees of freedom for between groups and within groups. So it's real simple. Between groups is k minus 1. Basically, you would have 3 groups minus 1 if you did have 3 groups. If it was a pre-test, post, or experimental control, then you would have 2 minus 1, and that would be 1. But here we had 3 groups, so 3 minus 1 is 2. Then you take the number of subjects in the groups, so that would be 30, minus k, which is in this situation 3, or if it was experimental and control, 2. Alright, but here it's 3, so then it would be 27. So 227. 8.8 again is the F value. It is not the mean. So you would probably write the mean, and then in parentheses put this F values. And then you write the alpha value. Now, you would basically write the alpha that the statistic reported. So if you look at the picture on the right, you can see the means are calculated below. The F for the different groups, the F value is 3.3, and then that value had a value of 0.031, indicating that you have a significant interaction between the different groups. Now remember too, this doesn't tell you where the significant interaction is. To do that, you're going to do what is known as a post hoc test. There's Tukey tests, there's different types of post hoc tests, and that will tell you where the means, the significant interaction will have occurred.